Okay, hi everyone, it's a pleasure to be here. So my title's on training intelligent game agents with deep reinforcement learning. So what can you expect? So if there was a subtitle to this talk, I would call it why deep reinforcement learning is so hard to get working. There's a fair bit of maths, and hopefully you've kind of had experience with deep learning and kind of understand terms like likelihood, stochastic gradient, etc. And you've had experience working with any autograd library. Even if you're kind of very kind of new to machine learning, you should hopefully be able to kind of get the intuition about kind of how we train agents in deep reinforcement learning. Yeah, so there's a lot to get through, and yeah, don't be kind of worried if you don't digest everything. So just a quick intro kind of about me. So I currently work in the research and development team at Founders Factory. I studied my master's in physics, and I'm very kind of obsessed with deep reinforcement learning, and hopefully I can kind of convey that kind of passion to you today. So the kind of outline for this talk is we're just going to have an introduction to what deep reinforcement learning is, markov decision processes. MDPs are the kind of backbone behind reinforcement learning in general. And then we've got three kind of classes of methods, main classes of methods used in reinforcement learning: policy gradients, value-based methods, and actor-critic style methods. And then we'll kind of conclude after that. So kind of just to start off, it's a good idea to see kind of where reinforcement learning fits into machine learning. So supervised learning is very much about kind of building a model that maps data to labels. And you've got a very well-defined task. Unsupervised learning is a kind of bit more broader. It's usually kind of involves kind of fundamentally understanding the kind of structural probability distribution of your data, and kind of lots of kind of techniques like clustering, dimensionality reduction, density estimation, generating new samples are fit into unsupervised learning. Reinforcement learning is about maximizing the rewards we get from the environment. So it's not entirely supervised learning. It's not entirely unsupervised learning. It's kind of fits, in its own kind of domain, because so the main task is that we're trying to kind of maximize. We're trying to learn a behavior or a policy in the environment that we're in. And so in supervised learning, you've already got the data to start off with. You've already got your labels. But we actually interact in the environment, and then we get data. So, and how we kind of choose to interact with an environment kind of changes what data we get, and that kind of changes how we learn. So a good example is kind of like when you've got a toddler, who kind of approaches a fire or a flame for the first time. They're not going to do it again because they've learned that action corresponds to some negative reward. Other things which we'll kind of see later is that the feedback can be delayed. We usually have a goal in mind, but we don't necessarily have to. And yes, so we don't have labels. Say we have the reward signals. So here's kind of a few kind of typical machine learning tasks, and let's kind of discuss about where they fall in. So kind of things like detecting tumors from MRI scans. I think it's pretty clear that you're using supervised learning because you need to have labels of, you need to have positive and negative labels in order to learn what's a tumor or isn't. Compression, so there's no labels in that, so it's unsupervised. Something like predicting house prices, you'd probably have kind of labels like, distance to a station and other kind of things which all affect the house price. And then you'd kind of build a function approximator that kind of maximizes the kind of likelihood of kind of getting the right kind of house prices. So fake news generator, that's a bit of a kind of, it's a weird one. So usually for language models where kind of, so language models like fake news generator it's unsupervised because you haven't got any true labels. You're learning the kind of probability, you're maximizing the likelihood that your tokens, your words, your sentences come from your data. The way you train it is very akin to supervised learning. So like if you've kind of seen how like a text generator is trained, it's trained like using like an autoregressive models where you've got your kind of probability distribution of all your tokens, and then you kind of factorize it out. And the label is your next token. So you're maximizing, for example, like the probability of token 10 given token 0 to 9 or 1 to 9. So and a toddler learning to walk. So that doesn't really fit into unsupervised learning because you're kind of learning you're trying to maximize your kind of reward in your environment, but it's not supervised learning as well because you don't have the labels to start off with, where you kind of interact with your environment. The toddler kind of changes how they move, etc., to kind of learn kind of how to walk and how not to walk. Okay, so I'll go through this quite quickly. So here's some examples of reinforcement learning. So the first one on top left is the kind of Nature article about AlphaGo, and I think that was one of the kind of first kind of big feats in reinforcement learning. You've got typically in kind of robotics, you would try to use kind of reinforcement learning, for example, to pick up an object. So you'd have rewards, for example, where you have -1 reward everywhere, but you have a large positive reward once the hand reaches the object. You've got personalized ad recommendations. That's an example of reinforcement learning. Self-driving cars. And sometimes you can train machine translation using reinforcement learning. Deep reinforcement learning is literally kind of deep learning plus reinforcement learning. So you have your kind of an environment where, so say you're trying to kind of solve a Rubik's Cube. You take an action, so that's something you can control. And your action is kind of governed by your policy. That's what we're trying to learn. So given the particular configuration, we're trying to learn an action that maximizes the total reward. We're trying to learn a policy that maximizes the total reward. So you have your Rubik's Cube, you take an action, and then you end up with a different configuration of your Rubik's Cube. So that's the next state. And you also kind of get a reward, that could be, for example, whether you've got, for example, one side all the same color, etc. And your goal is to kind of have a policy or kind of a set of actions which maximize your expected reward. And that can be kind of defined as kind of maximizing theta. So our policy is kind of parameterized by theta. That maximizes expected reward. So that's the probability of trajectory, and I've just kind of factorized it out. Okay, so I'll talk about this kind of briefly. So MDP kind of gives us a kind of formulation of how an agent kind of can interact in its environment, and it's the backbone of RL. So usually in MDP, you're in a particular state, and you can choose an action, and you get to another state. And sometimes you choose, you're in one state, and you choose an action, and you get to one particular state. But then the next time you pass by that state and you choose the same action, you enter a different state. So it's governed by kind of transition kind of probabilities. And the kind of key thing about MDPs is that they obey the Markov property, which is that the probability that you enter the next state, given your current state, is always constant. It's independent of your history. And that's something that kind of you really need in reinforcement learning. For things to work. So it's basically our sufficient statistic. So sufficient statistic is, so for example, in a recurrent neural network, your latest hidden state is, if you were kind of using RNN to kind of model a density, then your latest hidden state would be your sufficient statistic. So just to be a bit more formal, so our MDP has a set of possible states. So for example, all the places a delivery drone can be, a set of actions. So it could be the different kind of motions like moving forward, back, left, up, right, down, or kind of staying stationary. The transition probabilities, usually they're deterministic. So if you're in a state and you take an action, you'll usually always end up in the next state. But sometimes in different environments, they're not deterministic, and you need to kind of consider transition probabilities kind of carefully. And then you have your rewards. So the rewards are usually man-made. So in this case, for example, you could give a positive reward when the drone delivers the package to the right house, or a -10 reward, for example, if it delivers to if it's doing nothing or it's delivering it to the wrong house. And sometimes you have states which are terminal, which means that you kind of stop and your rollout is finished. And so an example would be if a drone crashes into a tree or if it completes its mission. So I'll just quickly run through this. So usually we don't want to calculate the exact sum of the rewards, because if you have like an infinite trajectory, then your rewards will kind of diverge if all your rewards are positive. So usually we apply a discount factor, usually about something like 0.999. So that the rewards kind of further away are still relevant, further away into the future are still relevant, but the total reward is still capped. And it also helps us reduce the variance as well. Usually we want to talk about the expected kind of return rather than just a return in a single rollout. So that's the Q function. And the Q function can be just written out like an expectation under your policy. So the pi here denotes your policy. So if you have a different policy, then you're going to have a different Q value because your total rewards will be kind of different, or your return will be different. Another useful kind of value is function is the value function, and that's similar to the Q function, but it's the expected reward given a particular state you're in. So we want to find a policy that visits the optimal value states, or we want to, equivalently, you should convince yourself that it's the same. We want to kind of have a policy that kind of always chooses the states that give us the maximum return. So we label them as Q star. So Q star is the optimal action value. Okay. Okay, so we mentioned that. Just a quick side note. So usually in the real world, we're working with partially observable MDPs, and they're MDPs that don't obey the Markov property. A good example would be, for example, if you saw, if you had a state of a picture of the car, then you know where its location is, but for example, you don't know whether it's driving right or left or backwards or forward. You don't know its acceleration. Usually, in order to turn a partially observable MDP into an MDP, we take into account its previous states as well. So for example, if you know where the car was like in the last few seconds, then you can work out its velocity, acceleration, and everything you need to know. So the first kind of reinforcement learning method we see is the policy gradient method. So it's called reinforce. And so remember, our objective is to is to find the policy parameter theta that maximizes the expected return in our environment. So we just call J the expected return. Usually we kind of use J for the kind of objective. And so we want to, in order to find a maximum, we need to take the gradient of it. But it's not so straightforward because you can't take a gradient of expectations. So we use something called a score function trick, or it's also called a log derivative trick or reinforce trick. And so if you kind of write the expectation as an integral, then you can take, so grad of pi can be rewritten as pi grad log of pi. And then we can take the pi out. And then we've got an expectation over an objective that we can, over gradients that we can compute. And the nice thing about this is that, when we write it out, when we kind of factorize out the kind of policy over a trajectory, then we can see that the states and transition dynamics are independent of theta. And so we can kind of get rid of them. And so we're left with this kind of objective. Okay, so, all right, so how do we train this? So we can write the expectation as just kind of sum, or an average. And the variance of this is very high. So one trick we can do is like we realize that the future actions don't depend on the past, don't determine the past rewards. So we only need to find out the rewards to go when we're at a particular state. So this is the Q function, by the way, as well. So that the thing inside a bracket can be looked at as a Q function when it's in expectation. Okay, so we're computing the maximum likelihood estimate of our policy. So when we're using autograd tools, this kind of objective is quite nice because it means that we can just get rid of the grad and just take the loss as this surrogate loss. And so it can be seen as kind of a product of two parts. So the first part is kind of very familiar in supervised learning. It's basically like a supervised objective where your actions are kind of the labels and your S is your kind of data. And so if you're working in a discrete action space, then your maximum, your negative likelihood is usually computed with cross entropy, or in the case where it's continuous, you kind of make the kind of assumption, you make the assumption that the probability distribution is Gaussian, and then you do the squared error between your target and your estimate. And so it's weighted by the return. So what this means is that we're kind of taking larger steps where you've got kind of bigger returns. Yep. Okay, so in the first notebook, there is a kind of a task on implementing the policy gradient. So you might want to kind of just take a few minutes to kind of have a look at that.
Sorry, where do we find these notebooks? Because it's not linked on the
Okay. All right, there should have been an email sent out with a GitHub link. Okay.
It's on the Slack.
Okay, 1 second. But I want to kind of show it here as well. 1 second.
The lost in base training intelligent game agents with deep reinforcement learning.
Yep. Yep. Yeah, sorry. Okay, 1 second. I think I'll show it in here instead. How do I switch to the notebook?
The notebook?
Yeah. All right, how do you do that?
Just swipe right and left while your cursor on top. Like 4 fingers.
All right, okay, cheers. All right, okay, so I'll just show it quickly over here. Yep, sure. Oh wait, that's not the good. All right, okay. Oops. Sorry, I can't see from here. Yep. All right. So, oh yeah. So I uploaded them as zip files. So, yeah. So it's lost in Bayes and then training intelligent game agents with deep reinforcement learning. And so, yeah, it's the first one, policy gradient. Okay. I think I'll just kind of quickly explain what's going on here right now. So we're using the OpenAI's gym environment. And so, with the environment, we can kind of do kind of rollouts. We can do rollouts and get the state actions and rewards as we're going along. And so over here, we kind of build a policy network. I tried this out with tf_layers.dense in TensorFlow 1.13, and for some reason, it was 10 times slower to do the forward pass. I'm not sure why. So here we're computing the policy. As a function of our states. So the size of that should be kind of the number of actions, which is 2. And over here, we kind of so our objective is here. So it's the kind of the mean of the log policy for actions times the kind of rewards to go.
Can you please zoom in, please?
Yeah, sure.
Yes, thanks.
Okay, that's not bad. And over here I've added, so you can ignore, you don't need to worry about this part too much, but I've added an entropy term because it helps with kind of exploration and making sure it doesn't kind of, the policy doesn't converge too quickly. Okay, and yeah, so you kind of compute that loss, and then you kind of update your network, and then you continue to do rollouts. And then kind of, so in here, the cartwheel, it's, the aim of the game is to kind of get it to balance. And so it did that. Okay, so I'll just go back to the reward. Does everyone have access to this, the link?
Downloading it to the requirements and stuff.
Okay, okay. Okay, I'm going to try to get back to the PowerPoint now. 1 second. All right, here. Okay. So, kind of, unfortunately, kind of the algorithm we're using is quite poor because the gradient of the variance of the gradients are quite large. So kind of what I did to kind of show it is I kind of compared two kind of gradient methods. One's called, the one we're using is reinforce, and the other one's called reparameterization trick. We can't use the reparameterization trick because we can't differentiate our rewards with respect to kind of our policy parameters. But I put it here. 1 second. So it's a kind of a weird objective, but you can think of it as like a fixed, like a VAE with a fixed decoder and ignoring the KL divergence term. So we're trying to find the encoder parameters that maximizes this likelihood, and both P and Q are Gaussian distributions, but Q's mean and standard deviation are parameterized by a neural network. So I'll just skip this part, and okay, so the black dot, so you can ignore the green dot. The black dot is the kind of destination of where the crosses are supposed to go. That's when the crosses kind of converge to the black dot, then we've kind of maximized our likelihood. So you can see that it kind of, actually you can't actually see this on the screen, but there's supposed to be like a disk showing the standard deviation, but like the points are kind of all over the place. So if you look at the means here, the kind of true mean is kind of 5, 5. That's the point it's supposed to converge to. But it's actually, so the cross is where the mean of our prediction is. It actually kind of just kind of ambles around it and kind of bounces kind of back and forth. And then kind of eventually kind of gets there, but it's still taking huge strides. And kind of if you have a lower learning rate than this, then it just blows up and you get NaN values. In contrast, with the kind of pathwise derivative or the reparameterization trick, you find that it kind of nicely, slowly goes towards the right direction, towards the black dot. Yep, so I just interrupted it now. Okay, so back to where we are. There's a very good paper which kind of explains how to take kind of gradients through kind of Monte Carlo kind of estimates. It's called gradient estimation using stochastic computational graphs, and it's by Schulman et al. Sorry. Okay, so can we train this on old data? And so when we're kind of collecting new data is very expensive. And so sometimes we might want to kind of reuse our old data. But if we look at this objective, it says that the trajectory or the kind of our kind of state selection samples kind of have to be in the kind of current policy that we're in. So that's why it's called policy gradient, because it's on policy. You can derive a kind of off-policy version, but it's really nasty. So you can use something called importance sampling, which is usually used for when you want to kind of reduce the variance of an expectation. So in this case, kind of pi bar would be our kind of policy under a new trajectory. Sorry, would be our kind of new policy and other new parameters. And an approximation to this gives us this really horrible kind of objective. And the kind of really bad thing about this is that, so this term over here is kind of exponential in your time. And so it can blow up or kind of go to zero. Also kind of using a baseline can also help you kind of reduce the variance of your gradients. And so the way you can show this is by taking the expectation of the grad log of your policy times b and showing that it equals to 0. Now you might be wondering like why we might want to do this. Well, if you take if you calculate the variance of this by taking the expectation minus the expectation squared, then you'll kind of find that the variance kind of can decrease with a good baseline. And a good baseline is typically an average reward, and we'll come back to that later. So the kind of pros and cons of policy gradient is that, so the one big pro is that you can learn stochastic policies. And the reason why that's good is, like, for example, if you've got a game of rock, paper, scissors, then if you have a deterministic policy, then like an opponent can easily exploit that by kind of, for example, if you always kind of decide to do kind of scissors after your opponent does rock, then the opponent can exploit that and kind of always win. We'll see kind of a good example in just a bit. You can work with discrete and continuous action spaces. So generally, it's hard to kind of modify your algorithm to work with continuous action spaces. But there's kind of no reason why we can't do both. And because in our objective, it works fine. The kind of gradients are unbiased. And so it means that you can kind of converge to a local optimum. Okay. And the kind of, on the cons, we've seen that the variance is kind of very high. We can take some measures to reduce that, like using a larger batch size or smaller learning rate. It's also not straightforward to kind of implement it with off-policy data. And if you've got an environment that's deterministic, then it learns less quicker than deterministic policies. Okay, so one kind of good example of a game I found is, so you're in an environment and each of these squares is a state that you can be in. Obviously, you want to get the kind of money back, and you want to avoid the skulls. Now, if you're using a deterministic policy, so in this environment, the environment is partially observable. So the state doesn't. So when the state's on one of the gray spots, it doesn't know whether it's on the left one or the right one because it sees a door either way. But if you're learning deterministic policy, then you have to choose one, and so you'll kind of be. So if you're on the left, then you'll kind of be stuck in that kind of loop, and you won't get out. But in the stochastic policy, you'd have like an even probability of going left or right. So we looked at policy-based methods. Now we're going to look at value-based methods, and the question is, can we omit the policy gradients completely? And so kind of we return to our initial objective, which is that we want to visit the Q values. Remember, the Q values are the Q values are given the state in action is the kind of expected reward from that state. And so we want to kind of visit the optimal ones. So when we're at a state and we've been presented with different actions, we want to go to the queue that's highest. And so we want to take the action basically that where we're always in the kind of optimal queue states. So obviously not all actions are equal. If we know the optimal action value, we've kind of solved the problem. So we can learn the optimal Q values directly. So we'll talk about that in a bit. So one method we can use is something called bootstrapping. That basically says that we can kind of get our kind of a better estimate of the value in our current state by knowing the kind of value in the next state. So the intuition is that the rewards flow kind of from the future time steps to the present time steps. Another way of looking at it is that the value estimates at higher time steps are more reliable. So for example, if you're kind of one step before a terminal state, then you've got a much lower variance because there's only a few actions that you can take and a few rewards you can get. But if you're at the start of your MDP, then there's lots of possibilities that you can of kind of rewards that you can get. So for a finite number of states, the Bellman optimality operator is defined as so B of the value state is the action that maximizes your reward plus gamma times. So this T here is the transition dynamics matrix, but you can think of it as an expectation of the kind of next values. And it can be shown that it's a contracting operator, and that basically means that if we keep applying the Bellman optimality operator, then we can kind of converge to the optimal value states. And so it also applies to Q values too. Unfortunately, when we're using deep learning, we don't have any kind of guarantees on the convergence. And to see why that's the case is that usually, so we're working in continuous states. So we don't kind of construct the matrix in typical Q-learning. And what we want to do is so Y here is the target value. So Y here is basically the maximum of the reward plus the next value step. And we want to kind of minimize Bellman error. And so there should be a B operator here. And basically what you can show is that when you have both of these contractions together, then you don't get a contraction anymore. But you can still kind of expect some kind of good results. And this problem is known as the deadly triad. And if you want to know more about it, you can look in Sutton and Bartow's book. Okay, so for deep Q networks, we have our Q function as the reward plus gamma times the maximum, the action that maximizes the maximum Q value in the next state. And we want to minimize this error. So I put kind of ice cubes kind of over this target value, this target Q, because we actually don't want to change. So we don't want to backpropagate gradients for our target value because we're using it as a reference. Unfortunately, we're not kind of learning a maximum likelihood estimation anymore. And that's because we're that's because our kind of target Y is no longer our kind of target Q value isn't accurate. It's still an estimation. And yeah, so the target Q value is biased. And the target Q values and the estimated Q values are correlated. So kind of just to understand the problem of instability in the Q learning a bit more, we can think of our kind of Q values as being parameterized. So we can think of our Q values as a net, where the net is kind of, where the shape of the net is kind of parameterized by theta, our neural network parameters. So when we have a high local Q value that's larger than our initial estimate, we update our parameters using stochastic gradient descent, and we pull the net higher. Unfortunately, when we pull the net higher, we also pull the neighboring points as well, and we might not necessarily want to do that. So if we upgrade a policy in every time step, we effectively keep kind of increasing the net, pulling up the net in the same place. So one way to kind of mitigate this is by kind of randomizing the kind of states, actions, rewards that we kind of feed in to our objective. So this is called a replay buffer. So the replay buffer basically stores your state, action, reward, and next state tuples. And then when you want to update the Q value, you take a tuple from random, And that kind of ensures that you're not picking the kind of the tuples that are next to each other, and the kind of states that are next to each other, and the actions that are next to the state action pairs that are next to each other. And so you're not getting that kind of problem we kind of discussed before. It's really easy to implement, and there's no kind of correction term. And so basically we just kind of changed the kind of the expectation part. So now it's our tuples are coming from the buffer. So that's our objective. Okay, so another way we can kind of mitigate the issue is by decoupling the target network parameters from the estimated queue. So there's kind of two places where we can get the target parameters. So one is by having a totally new queue network. So the same queue network kind of trained on different samples. And so that would kind of help kind of increase stability. Or we can use what's usually used is an older saved network of our queue values. And the downside to that is that the older kind of queue values are still somewhat correlated with the current queue values. Sometimes you can use kind of polyac. So So one way of kind of adjusting the network parameters is using polyac averaging. So we're just slowly updating our theta parameters. And so you can see an example, so this diagram here as well. So after every k number of steps, you kind of transfer your current theta to your target q theta. Okay, so choosing an exploration policy for rollouts. So when we kind of run the algorithm, we need to make a kind of decision about kind of what actions we take. So kind of initially you might think that you want to take the actions that maximize the Q value, the next Q value, because then you're more likely to kind of go into regions with a higher reward. But sometimes what you might find is that if you explore kind of uncharted areas, they might have kind of much higher Q values. And usually kind of a good exploration policy can be kind of difference between a really bad algorithm and a really good algorithm. So one common one is called epsilon greedy. So with a certain probability, you choose the maximum Q value. You choose the action with the maximum Q value. Otherwise, you kind of choose any other action at random. Okay. There are some other kind of exploration kind of heuristics. One common one is called Boltzmann exploration, where you just basically take the action kind of proportional to the exponential of the Q function of your different actions. Okay, so that's a kind of overview of deep Q learning. So you kind of save your target network parameters, you kind of run a rollout, and you can kind of choose what policy you use to run a rollout. Then you sample some tuples from your replay buffer, and then you kind of train this loss. So there's different things that you can tweak the algorithm in different ways. So you can choose to, for example, to take a loop from, say, 4 to 3 in a cycle. If you wanted to, if, for example, kind of gathering data is very expensive. Okay, another problem in kind of Q learning is this kind of problem of overestimating our Q values. So usually when we're kind of trying to minimize this Bellman error or temporal difference error, we're taking, we're kind of constantly kind of minimizing this entire Bellman error. But actually kind of what you want is, so ideally, in an ideal world, you kind of want, so our Q values are noisy, and you want to take the Bellman difference of the kind of true Q value and of the true kind of Q values for your target and current state. And so ideally, you'd want to kind of take the kind of expectation of those Q values. But what you're in fact doing is you're taking an expectation over the maxes. And that basically means that you're kind of overestimating your target Q value. Okay, so in double Q learning, they kind of get around that, this kind of issue of kind of decorrelating the noise in our kind of the actions we take from the noise and the values. And it's by kind of a subtle method. And they basically choose a different network to select action from the network to kind of evaluate the values. So that's our kind of current, that's our current target value. And just the one thing we change is now we kind of take the argmax over the kind of the current Q value parameters rather than the target parameters. And that basically works to kind of decorrelate this noise issue. And so in the double Q learning paper, they found that, so I'm not sure how they got their true value, but what they found was that in double, when they kind of applied that fix, then the value estimates were kind of much more accurate. Okay, so, so there's a kind of a notebook for Q learning as well. 1 second. So you might just want to take a bit of time to kind of look into that. So it's this one here. It's called Double DQ and then Breakout. I think I added the 3 later on for my own reference. So you might just want to take a couple of minutes to kind of look at that. Okay, so So I can't play the video for some reason. Okay, so there's kind of a few things I just want to kind of point out in here, and that is, so you're working in an environment of breakout. Now, this is an example of partially observable MDP, because given our current state, like this picture is a state that would be kind of usually fed in to our MDP. Now, from that state, you don't know whether it's moving right or left, and so it's a partially observable MDP. And the way usually they for Atari games they kind of obviate this issue is by stacking the previous frames as well. So over here, you've got 4 previous frames that are kind of stacked together. Yep, so here. And the other kind of subtlety probably that you might not notice is that so our Q function is a function of our state and actions. But for the network, we only input our states. And we kind of input only our states because we want to get the Q function for all our possible actions. And so the output of a network is the Q functions for that particular state and all the different actions. And the reason why we do it this way is that it's very easy to do the argmax, because then you can just select the highest Q value. And the other subtlety with so with normal kind of DQN, the target values are kind of straightforward to kind of implement. And the only thing you need to do for double DQN is just get the argmax for the other network and of the kind of current action values, Q values, so here's another thing as well. So we want to, so we use tf.stop gradient for our target values because we don't want to backpropagate through them. But actually, in this particular case, the way it's set up, you don't need to use tf.stop gradients because when you've got the copy of the network, the gradients can't backpropagate anyway. Okay, so all this kind of go next. So the kind of last kind of group of algorithms is called that we're looking at is actor-critic algorithms. And so basically, we've looked at policy-based methods and we've looked at value-based methods. And we want to know, is there a way of kind of combining both of them together? So with the policy-based methods, we saw that they were unbiased, but the variance was quite large. And the kind of intuition for why the variance was so large is because when you're taking the expected returns, when you're taking the rollouts, you could have lots of different possible returns. So you can have, for the same policy, you can have one very high return and one very low return. But for Q values, we found that they were biased because of development operator that can't be applied for deep learning. But the variance is also, the variance, however, is very low. And the reason for that is because you're just taking the mean squared error between your current Q value and the estimate of your next Q value. And your next Q value won't change much over your algorithm as you're training. Okay. So if you look at kind of our kind of objective the gradients we want to take, kind of in place of phi, we have the kind of expected return. So if we take phi as just a kind of expected return as we're kind of running our policy, then we have a policy gradient algorithm. And we can apply a kind of control variant or baseline to reduce the variance. However, this is the exact same thing as the Q value. So the reason why I've put the Q value over there as well is because you can parameterize your Q value with a neural network. And so it'll be biased, but the kind of objective is the same. But you'll have lower variance. A kind of a good baseline to use is your value at your current state. And so when you take Q minus V, it's called an advantage. And the kind of intuition behind that is that your kind of advantage is your advantage at a particular state and action is, so if you take a particular, so at a particular state, your advantage is how much better is a particular action compared to any other action. And we saw that we can apply the kind of baseline as long as it's kind of independent of your actions. And so your expectations won't change. The expectation of the gradients won't be different, but it'll just be lower. The variance of them will be lower. And so with the advantage there, written over there as Q minus V, you can train it using two different neural networks. If you wanted to only use one neural network, then you can just write Q as your, so remember your Q is your Q value is your kind of the reward you get at your, after you take a particular action, plus the kind of sum of the rewards if you kind of run the policy, the expected sum of the rewards if you kind of run the policy. And so that's just basically rewards plus your discount factor times your next value state. And so this is a kind of typical kind of algorithm for Q actor critic. So kind of one thing to kind of point out is that, so you've got two different neural networks, and you need to update Q. So you're updating Q using the Bellman error as well, or the temporal difference error. And so this objective is still biased because of that Q, but the variance is greatly reduced. And here's one for the advantage actor critic. And it's basically very similar, except we've taken the advantage to be, so we've just taken, instead of the Q over here, we've just used, so on the last line where it says theta, you update the kind of theta using advantage times the gradient of log pi. You just change the Q to your advantage. So I think, yeah, so there's a notebook for this particular algorithm, and that's the last notebook on there. So you might want to look at that. It's called, yeah, Advantage Actor Critic with the Kung Fu Gym environment. So there's not much, so you're trying to, different neural networks, so one for your policy and one for your value. But other than that, there's not much that's different from the policy gradient. Okay. So kind of, I've trained it, and so if you get time, you can have a look at it as well. And so it kind of works pretty well. So I'm going to go back to the slides. So let's take a look at kind of one of the advantage estimates. Okay. So if we look at our advantage estimates again, so we were trying to minimize the temporal difference error by kind of minimizing the error between the current Q value state and your next value state. You can get a lower, you can expand your next value state as a reward plus gamma times the next value state 2 steps on. And you can keep doing that. And eventually you basically get the policy gradient with a baseline, which is your value state. And so kind of the kind of range from here is that you have a high bias and low variance at the top, but at the bottom you have a low bias and high variance. So at the top, at the bottom, the reason why you have a high variance is because the rewards from your rollout can have a high variance. So under the same policy, you can have lots of different. You can have a kind of a great range of returns. And the reason why you've got a low variance at the top is because there's only kind of the kind of variance you get from your value state, your next value state, and the kind of reward at the next when you take an action at that state. Okay, so I'll just kind of skip this. So so kind of one of the more kind of advanced algorithms is called DDPG, Deep Deterministic Policy Gradient. And it looks at the kind of, so if we look back at Q learning, we have to take an argmax over the Q values. However, if you're working with a continuous action space, then you can't really, it's very difficult to kind of find a way to take an argmax. And so the intuition behind DDPG is that you want to take, so you use a deterministic policy, and your deterministic policy is kind of dependent on your state. And you just kind of differentiate your Q values. So you just basically kind of take the derivative of your deterministic policy with respect to your theta from your Q values. Because you want to kind of take gradient ascent to kind of make sure you get a policy that kind of maximizes the Q values. And so the loss is just basically, so you've got two losses. So you've got your loss from your critic, which is just computed with your Bellman error. And then your loss with your actor, which you can do using chain rule. So I won't really go into this other algorithm. It's called I won't go too much into it. So it's called trust region policy optimization. And basically, it kind of looks at the kind of the variance, the kind of high variance issue in usual policy gradient. And what it does is it tries to, so the kind of intuition behind it is if you've got a policy which is parameterized by theta, if you kind of change theta by a small amount, then there's a possibility you can have a completely different wild policy, especially if it changes, especially if it changes the policy especially if it changes the kind of actions towards the beginning of a trajectory. And so the kind of solution is, well, why don't we constrain the kind of the policy, our new policy from our old policy with a KL divergence, and it's constrained so that it's less than delta, and it works much better than all the algorithms we've seen so far, including DDPG. So kind of lastly, I kind of want to talk about why deep reinforcement learning isn't really kind of ready to be kind of deployed at large. It's really hard for a number of reasons. So classical robotic techniques kind of in optimal control outperform RL already. It's too data hungry. Usually kind of when you're working with complex environments, then you have to wait a very long time before you see your kind of rewards starting to pick up. It also requires a reward function, and that's kind of man-made as well. And so sometimes there's environments where it's very difficult to see kind of how you can kind of allocate the rewards in the best way. You can fall into suboptimal behaviors, and I'll show one example of that on the next slide. It's poor at generalization and transfer learning. It's very sensitive to hyperparameter tuning, and this can make it really frustrating because usually you don't know. So if you've built a new algorithm, then you have to wait a very long time before you can work out whether your algorithm is good or not, because for a long time you're just going to have your kind of rewards kind of be kind of like close to zero, or kind of like plateaued to begin with. And the kind of variance and noise issue in reinforcement learning is kind of very high. So here's an example on the Mujoko environment. I encourage you to kind of get it if you can. So if you're a student, then you can have it. You can kind of download it for free, and it's compatible with OpenAI Gym. And so I think for this particular environment, they used an algorithm called normalized advantage functions, and it kind of dropped into a kind of suboptimal policy. And when you're in a suboptimal policy like that, it's kind of very difficult to get out of it because you're in a relatively high reward region. So some kind of research areas ongoing are kind of multi-agent reinforcement learning, model-based reinforcement learning. So multi-agent reinforcement learning is when you've got lots of different agents, and they could be kind of cooperating or vying for some goal. And it's quite challenging because you're not working you're not really working in MD. You're not really working because your environment is kind of dynamic, and so you can't use, for example, your replay buffer. You can't use the states and actions you used before because your kind of environment is kind of being, it's turned very kind of dynamic because of the introduction of other agents. So model-based RL is another area where you're learning about your model. So for example, you could be learning the transition dynamics, and sometimes that can really kind of boost your performance. Meta RL, which is about kind of learning to reinforcement learn. Representation learning, kind of effective exploration techniques. Imitation learning, so an inverse RL, so kind of given a policy, can you kind of reverse engineer what the rewards in the environment should be like? Transfer learning. Okay, so I just kind of like to end this off with a kind of a nice quote I found. It's by Alex Zerpan, who works in Google Brain. So several times now, I've seen people get lured by recent work. They try deep reinforcement learning for the first time, and without fail, they underestimate deep RL's difficulties. Without fail, the toy problem is not as easy as it looks, and the field destroys them a few times until they set realistic expectations. So thanks for listening. That's the end of my talk.